Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we're going to learn a new topic, continuous from last topic. This is a multiple linear regression. So last class we already learned about correlation and simple linear regression. So today we're going to look into what if we have more independent variable. So it come with multiple linear regression. So now multiple linear regression or MLR is the estimation of the linear relationship, right, between dependent variable and more than one independent variable or covariate lah. So independent variable we also call as a covariate when the independent variable is a continuous variable. So is multiple linear regression is always applied in a exploratory studies or confirmatory studies, and the outcome variable should be numerical variable. So numerical variable means that as I emphasized on the last lecture, the dependent variable should be always continuous quantitative variable. If independent variable have a numeric, so this is what we call as a multiple linear regression. If independent variable are combination of numerical and categorical or categorical data only, so this is what we call as a general linear regression, right? So but in this case, in this topic, we are only focused on a multiple linear regression. We are not going to touch on general linear regression, right? So this is a formula equation when you already conduct the multiple linear regression model. So this is going to be your equation. So y is your dependent variable, beta naught here is your intercept, right, and beta 1 is your coefficient for independent variable number 1. This is a independent variable, and beta 2 is a coefficient for independent variable number 2, and x2 is our independent variable number 2, and continuously. Right, example of multiple linear regression. So for example, let's say we want to find the relationship between age, weight and height, and PEFR means peak exploratory flow rate. Right, if looking at relationship of individual independent variable to PEFR, so this is what we call as univariable analysis, right? As we have doing on the last lecture, we do one by one independent variable into one dependent variable. So this is what we call as univariable analysis or simple linear regression. By doing a simple linear regression only or univariable analysis only, it may not be a biologically sound good, right? Always in a clinical studies, right, or medical studies, they're always having a relationship with others, co-founders or moderators, right? We need to look at the relationship when all variables are considered at the time, which is what we call as a multivariable analysis. So multivariable analysis is our multiple linear regression, right? So we want to look at the relationship of when all variables are considered at the time towards the outcome PEFR. Right, we can also look into the present of confounding and interaction lah. Right, when we do multiple linear regression, we're going to go to the process to look into the confounding and interaction, right? So this is a step in multiple linear regression. So first step is we always start with data exploration and cleaning. We're going to explore the data. We need to understand the nature of the data, right? And we're going to do some cleaning process if you need. And then step number 2, we're going to do univariable analysis. univariable analysis is simple linear regression. We're going to proceed with the step in simple linear regression. And after that, step number 3, we're going to do a variable selection. Variable selection means that we're going to choose the importance variable in simple linear regression, and we're going to include it into a variable selection procedure. So in the variable selection procedure, we're going to apply at least 3 selection procedure. For example, forward selection, backward elimination, and stepwise selection. Right, so this is what we call as preliminary main effect model. Right. For step number 4, we're going to check for multicollinearity and interaction. Right, so this is what we call as a preliminary final model. And the second last, step number 5, we're going to check the assumption line. So in multiple linear regression, we're going to add another assumption, which is I. Right, remember, line L is for linearity of the dependent variable, and I is for independence, N is for normal distributed, E is for equality of variance, and I is for the independence of linear covariates. So this one we are already done with the step checking assumption. So this is what we call as a final model, right? And then step number 6, we're going to interpret and do a presentation lah. Right. So now let's look at the. I'm going to go through for simple slides dulu. Nanti sebelum tu baru kita tengok dia punya coding. Right. Step number 1 tadi kita kena tengok data exploration. This is I'm doing in SPSS. Step number 2, we're going to do simple linear regression for all variable. So do simple linear regression for age and PFR, weight and PFR, and height and PFR. Right. So we're going to select the p-value, the importance of variable that significant. In this case, significant we refer to 0.25 based on Hosmer and Lemshow says that when the p-value less than 0.25, we're going to consider it into the variable selection procedure. Right. Okay. Step number. Next slide. So this is we do a simple linear regression for age and PFR. Right. Let's do one by one lah. Right. Sebelum I proceed, you are my voice clear? You boleh nampak my slide? Can you understand? Do you have any questions so far?
So far tak ada, sir.
Alright, good. So remember data set that I gave you in Google Classroom. So we're going to use a data set PEFR MLR.dta. Right. So first step is to set your working directory. So I'm going to set my working directory. So make sure your working directory contain your data set lah. So let's look at the data directory. What do we have here? So I'm going to call pafr.dta. So pafrmlr.dta is a startup file. So I'm going to use a library, Heaven. So you can also use a foreign library to call the data. So I'm going to call it as a data1 and then read underscore startup and paste. Oh, sorry. I'm going to copy the file name and letak dekat sini lah. Alright. So now I already called the data, right? So let's do some data exploration, right? Refer to the slide step that we're going to conduct. Oops. Yep. First step is to do a data exploration and cleaning, right? So now data exploration. Right, so let's look at the dimension of the data. So we have 1369 observation with 5 variables. So what are the variables available? Let's look at the names of data 1. So we have age, weight, height, PFR, and INS. I'm not sure about INS. So let's look at the head of data 1. What is INS? So INS basically is a run number, I think. So let's look at the structure first. Structure, str data 1. So now look at age. Age is a numeric variable. Weight also. Weight is in double, right? So it's also numeric, right? Double means it's kind of a quantitative data juga. Height also in double, right? PFR also in double, means that there are no decimal point lah. So they are not really continuous, but there are this is a quantitative data lah, numeric. But INS is not relevant to us. We're going to drop INS from the data set. So let's say I'm going to drop INS variable from object data 1 lah. Right, so data 1 remove number 5, right? So I'm going to remove variable number 5, which is INS, from the object R. So now let's look at the distribution of the data set, right? Even though this is not really a requirement for linear regression, we just want to know what type of distribution for each variable. Right, so let's look at histogram data 1. Age supposed to be a skewed data set. So yes, this is a skewed to the right distribution. And histogram data 1 weight should be, this is not really normal distribution, right? So it doesn't matter whether this is not normal or not, normal distribution or not, because this is not really a requirement for linear regression. The normality assumption only apply when we already develop the model. We're going to measure the normality on error or residual value. This is, we just want to know, right? So this is not really normal distribution lah. So if we do a Shapiro test data 1 age, we will see that there are not normal distribution lah, right? Let's continue with data 1 weight, also not normal because the p-value is less than 0.05. Shapiro data 1 height, see, is not normal, and we already expecting this one lah, because by eye we already look at the histogram, we know that this is not normal distributed lah. So PFR distribution variable also not really normal distribution. So now let's see the mean and standard deviation, right? Checking mean and standard deviation. So I'm going to use library table 1. library table 1. So I'm going to use function create table 1 data 1. So they will data equal to data 1. So they will give us the mean and standard deviation for each variable. So mean for age is 65 years old with a standard deviation 7.998, means that this is going to be for 50 years old. The minimum value is 50 years old to the maybe 199 years old. Weight is mean of weight is 53.69. So the minimum value is maybe 30 something to 80 something, right? The standard deviation is 8.95. So we need to understand the mean and standard deviation, and then check the distribution of the each variable, so for us to understand the nature of the data. Then after that, we're going to fit. This is our step number 2. We're going to fit simple linear regression. So we're going to fit a simple linear regression for each variable, right? So let's say I'm going to use the function lm, right? Lm. So I'm going first, before I start with the lm, I'm going to attach data 1. So I don't need to call data 1 dollars with the dollar sign again lah. So if you see the Shapiro Wilk test ni, I call the variable with a data 1 dollar sign. So when I attach the data, so I no need to write down data 1 dollar sign. So I just call the variable name. So let's say model 1 lm PEFR and then H, right? And then summary model 1. So if you can see, for the linear regression, the simple linear regression for H and PEFR, the p-value is less than 0.05, means that this is important variable, right? Now let's look at a model 2 lm PEFR and then weight summary model 2. So by looking at the simple linear regression model, weight also a significant variable. It's an important variable. It has a relationship with the PEFR since the p-value is less than 0.05. But if you look at into, even though the p-value is less than 0.05, if you look at the r squared is quite low, right? Means that there are something else should be import into the model, right? Let's look at the model 3 lm PEFR and then height, right? Summary model 3, right? Now same as height and age, weight and age. So height also reported to be found to be very significant variable towards PEFR, right? Since the p-value is less than 0.05, right? So now by looking at the step, right? First step we already done, data exploration and cleaning. Second step is univariable analysis, which is a simple linear regression, right? So third step is a variable selection. So variable selection based on Hosmer and Lemshow, it says that even though the variable is not, if we have a non-significant variable in a simple linear regression, we're going to look at the p-value. If the p-value is less than 0.25, we're going to include it into the variable selection. So I'm going to write here, for variable selection, so we would only select variables that have p-value less than 0.25 in simple linear regression to be included in variable selection procedure, right? So even though the variable, if you have a insignificant variable in simple linear regression, if the p-value is still less than 0.25, not 0.05, 0.25 means that it's not significant. So we're going to consider it into a variable selection procedure, right? So if they're more than 0.25, mean going to exclude it. Alright, so now we're going to do a variable selection procedure, right? So variable selection procedure, we're going to test a selection procedure. First selection procedure is a forward selection, backward selection, elimination, and stepwise selection. So let's look at the slide first. Yeah. So now variable selection in multiple linear regression, selection is done by automatic procedure. So a number of methods available, as I said before, we have forward selection, backward elimination, and stepwise procedure. So all methods should be done and select the model with all variables. We're going to select the model with all variables that's significant, right? All the variable that's significant that we call as a largest model as a preliminary main effect model. So in this stage, when we have done a variable selection, so it is called as the preliminary main effect model, right? So now the principle in a variable selection. So the principle, we have three principles: the principle of fit of the model, right? Principle of parsimony, right? And the last principle is biologically plausible, right? So principle of fit of the model means that we're going to select the model that with a higher number of variable, the model fitness getting better and better lah. So we're not going to do this because when we include many variable into linear regression, if the model fitness is going to be better and better lah, of course, right? It's going to be overfit. So we're going to use principle of parsimony, means the principle with the least number of variable and those variable are significant, right? We're not going to include others insignificant variable into the model, right? So we are focusing on principle of parsimony. So that's why we're going to use a variable selection procedure lah. And then in some case, biological possibility is must be considered, where the variable are proven significant by literature. For example, let's say a heart disease and smoking cigarette, right? So if you test with a model, let's say heart disease, you test with a high exercise, you test with food intake and so on, and smoking. So turn out when you do analysis, it turn out that smoking is not significant in your model, but in literature most of them are telling us that smoking is very significant and proven related to heart disease. So you need to consider it to include into the model, right? Okay, so for this example we're going to use a principle of parsimony. So now to create to do a variable selection, first step, we're going to create empty model. first we're going to create empty model. Means that let's say empty. So empty means that we're not going to include all the independent variable inside the model. So it means that the first dependent variable PEFR will going to 1, right? So there are no independent variable inside. Data equal to data 1, right? So summary empty model. So not in this model there are no independent variable. They just only intercept value lah. So you need to know the procedure of selecting in forward selection. In forward selection, it start with the empty model. You're going to include one variable, one independent variable, another independent variable to test the variable. Right? From the empty model, then you're going to include. But for backward elimination, you're going to start with the all model inside the data, all the variable inside the model, and then you're going to eliminate one by one. That is what we call as a backward elimination. For forward stepwise selection or stepwise procedure, it will start with the fit all, or you're going to start with empty the model also can. So you can do either way, right? You can start with a fit all variable in the model, or you can start with the empty model, right? You can do either way. So now we're going to look into the second step. Is going to create full model. Create full model. So full LM equal to PEFR, and then dot means that you're going to select all the variable in the data equal to data 1. But you need to make sure our data set only contain the variable that we want to select, right? So just now remember at the beginning we have INS here, so I already remove INS variable here. So this is the variable that available in the data set 1 lah. So that's why we can use dot here. Tilde dot means that we're going to select the rest of the variable in the data set, right? So now summary full, so it will include all the variables, right? So let's look at the formula. Before I forgot, the formula of empty. So in formula for empty model, there are no variable inside. So formula for full, so it will include all the variable, age plus weight plus height, right? So now step number 3. Now we're going to do a forward selection. Right. Forward selection, let's say forward. So I'm going to use forward 1 lah. Forward 1 step. This is a a full model. Sorry, this is going to start with empty model kan? Empty model, because in forward selection it start with empty model. Direction forward without S, and then we're going to specify our scope should be equal to formula full. So we're going to specify until full lah. So the ultimate objective is to fit all the model, all the variable. So now based on the forward selection, so it start with the AIC 1 13,107, and then this is what we call as PFR empty model. When we try to include weight, right? When we try to include weight, the AIC means the error become lower, right? Means weight is important variable lah. So then when we add another variable height into the model, the AIC become more lower, means that height also important variable, right? And the last step is it or include age into the model, and the AIC is became lesser compared to previously. So age is also important in the variable model. So if you can type summary forward one, so means that now all the variable are included into the model, right? Because all the variable have a significant relationship with PEFR. So if you look at the p value also less than 0.05, right? So now let's look at backward elimination. We need to do all the variable, all the procedure. Right, for backward elimination, let's say I put it as a backward. So start from full model. Why full model direction should be backward lah. So now since backward elimination start with the full model, all the variable are inside. There are no variable are excluded or eliminated from the model, means that all the variable are important, right? So there are no elimination. So this is the final model lah for backward elimination. So let's say summary backward. It will give backward without S. It will give us the same model as if we found in forward selection lah, right? So now step number 5, we're going to do a stepwise procedure. So stepwise can do either way, whether you can start with the empty model or start with full model. So I'm going to start with a full model stepwise, right? So step full, so direction both. So both mean they are going to exclude and include, right? So they're going to do both procedure lah. So same as backward elimination, so none of the variable are excluded, right? So you're going to get the same variable lah, right? So this is a very beautiful data set, right? So if you do a real data set, when you do a data collection by yourself, so you will find some variable that are not really important, right? So next step is our preliminary main effect model. So we already obtained our preliminary main effect model, right? So our preliminary main effect model is all the variable inside the data set lah. Let's say I put PEM, preliminary main effect model. So this should be PEFR, age, weight, plus height, right? So this is our preliminary main effect model. Now the next step is when you already do a variable selection. Step number 4 is to do a two-way interaction checking, right? in two-way interaction checking, right? So interaction term need to be compute, right? So in SPSS, the transform got but then compute lah. This is SPSS, but we're going to use R. Very simple. We need to be biologically meaningful, right? If they are not biologically meaningful, then it's not possible to do an interaction lah. So interaction term is added to the model as independent variable and check only one term at one time. So we're going to input one interaction at a time. Right, so if interaction term is statistically significant, then the model should be main effect term with a significant interaction term. Then this is going to be very hard to interpret lah. Right, so now we're going to check for two-way interaction. So we're going to input our interaction term one by one in the model. So how are we going to do interaction term, right? So we're going to input age multiplied with weight after the age, weight and height, age and multiply with height, weight multiply with height. So let's look at interaction 1. So LM PEFR age plus weight plus height plus age multiply with weight. So remember, if you can see, now I already add a new term, which is two-way interaction term inside the model, right? So now look at the summary of interaction. Why my keyboard macam ni interaction ada tak? Okay, so now if you look at the model, age, now when you include the interaction term age and weight, so age, individual age became not significant, right? And weight and become less, the p-value is become larger, right? But still insignificant. But age and weight is totally not significant because the p-value is less than 0.05, is more than 0.05, right? Let's look at interaction number 2, right? LM PEFR age plus weight plus height plus age multiply with height. So if you can notice here, for the second interaction model, age is multiplied with height, right? So I'm going to do summary interaction 2. Now, interaction. Salah tulis ke? So I tak run lagi. Alright. Where is summary? Oh yeah, dot summary. Cannot find. Okay, now if you can notice here, height is become not significant, age also become not significant, and age multiply with height, the interaction term with age and height is also not significant. So it should be not in the model. So let's look at interaction number 3. So LM, let's say I copy this one first. So instead of putting age and height, I'm putting weight and height. So now the last interaction term is weight and height, right? So summary interaction, right? So if you can see here, age is significant, less than 0.05, but weight and height is became not significant, and the interaction term between age and height is also not significant. So means that based on the three interaction model that we already compute, we can conclude that these interaction terms are not significant and should not be in the model. And we can also interaction all. We can also check interaction term for all interaction term at once in the model, but it's not really suggested from the book, right? So let's say I'm going to show you how to do that, but if this is not the best way to do lah, we need to do one by one lah. So I'm going to put age plus weight plus height. So then I'm going to input this one and 2, maksudnya power 2, right? Summarize interaction all, right? If you put all the interaction term in the model, it also indicate that the interaction term, all the interaction term are not significant as well, right? So this is preliminary final model, but not yet. We need to check for since all the interaction term is not significant, we're not going to include the interaction term. And then next step is we're going to check for ill conditioning, checking for ill conditioning or multicollinearity. Right, multicollinearity means that we're going there is a significant relationship or correlation, a very strong correlation between independent variable and independent variable. So to check a multicollinearity, let's look at the data slide. Right, so to check multicollinearity, we need to check whether independent variable in the preliminary main effect model is correlated or not. So within independent variable have a correlation or not. So if so, there are high chance of getting inaccurate p-value with wide 95% confidence interval of regression coefficient lah. So normally in previously, maybe you heard that when you have multicollinearity, you need to exclude the variable from the model. Actually, no way to do that. So what if that variable is very important? If you exclude that variable from the model, then you will lose the information, right? So never exclude multicollinearity variable from the model. Instead, what you need to do is you need to change your method of analysis. Instead of using a linear regression with a least square method, so you need to do some penalizing of the method. Means that you're going to use a ridge regression or lasso linear regression, or we can use either elastic net linear regression. We can put some penalization procedure that can accept a collinearity. Means that you have, when you have a collinearity, so don't carry forward with the simple multiple linear regression with a least square method with the current procedure ni. You need to change your analysis using a lasso linear regression or ridge linear regression or elastic linear regression. So that is a procedure lah. Never exclude collinearity variable, right? So if the collinearity exists lah, you need to change the method of analysis. If does not, then it's okay lah. You can carry on. So important variable may have been removed. This is not the correct way lah. I'm going to strike through, right? So now we're going to look the VIF, means the variance inflection factor, right? If the variance inflection factor is more than 10, then we can say that multicollinearity among independent variables, right? right? So if we can, we also can check for tolerance, right? If the tolerance is less than 0.2, right? So then the multicollinearity among independent variables, right? So now, so we already have a preliminary main effect model. Doesn't change anything because we're not including two-way interaction into the model, right? So now we're going to check for multicollinearity. So if you want to check multicollinearity, we need to use some library, MC test library. So if you don't have the library, please install the library. So in this library, we're going to use a function called as imcdiag library. So we're going to include the preliminary main effect model inside the function, right? So now in this result, it shows us the individual multicollinearity diagnostic result. It gives us the VIF variance inflection factor and the tolerance value and others statistic measure lah. So if you look at VIF for age, weight and height, the VIF value is 1 point something. So if you look at the procedure, the cut threshold, if VIF is more than 10, then we can say the multicollinearity exists lah. But now the multicollinearity does not exist because the VIF is less than 10. And if you look at the tolerance also is more than 0.2, so we can say that the multicollinearity does not exist. Okay, alright. So I hope you understand. Even though dia letak kat sini, maybe dia ada benda lain yang nak sebut lah. But that is our preliminary final model. So we can state our preliminary final model, right? So let's say I letak pre-final, still the same. The variable all the same, right? So let's say summary pre-final. This is the model. Let's say confin pre-final, right? So this is the confidence interval. The next step is we need to check, after we already checked the multicollinearity, we need to check for assumption of the model, right? Assumption of the model. So we need to check for linearity, right? So for linearity, so there are one additional assumption lah, right? For linearity, it's still same as a simple linear regression. We're going to do a scatter plot, residual versus predicted value XPYR. Remember, XPYR means that, and on x-axis we're going to put the predicted value, on y-axis we're going to put the residual value. So then we're going to check for independence. This is settled during design stage, sampling design stage. And we're going to check for normality of the response variable. Either we're going to use a histogram with normal curve of the residual. We're going to check on the residual, right? Oops, let me highlight this one. And also we can use a box plot of the residual, or we can do a diagnostic test lah. And then we also can use, we need to check homoscedasticity, equality of variance. This is the same step as a linearity, right? So we're going to use a scatter plot of the residual and predicted values. And the last assumption is to fit independent numerical variable, only for numerical variable. So we're going to look at the scatter diagram or scatter plot by using XI YR. Means that X axis we're going to input the individual variable, Y axis should be residual variable. Right. Now let's try to do checking a assumption. Now we already have a pre-final model. Let's say we look at the names of pre-final model. In this pre-final model, they give us a coefficient, residual, effect, rank, df residual, and so on lah. So now, first step, we're going to check for linearity and equality of variance, right? So I'm going to plot for, so remember, for linearity and equality variance, XPYR. X as is should be predicted value, Y as is should be a residual value. So pre-final, this is a predicted value, fitted value, and pre-final residual value, right? So then I'm going to rename X lab, it should be equal to predicted, and Y lab should be equal to residual, right? And then I'm going to put the title of the chart should be linearity and equality variance for pre-final model, right? And then maybe I'm going to change the color of the scatter diagram. Let's say I'm going to put this color 58 ACFA, and then maybe I don't want the frame dot plot. This is a condition lah, apa-apa yang nak letak lah, right? So this is the scatter diagram. Let's say I letak app line h equal to 0, means that I'm going to create a horizontal line. LWD should be equal to, means I make it thicker, and color equal to red. Small letter h. Yeah. So by looking at the scatter diagram, right? If you look at here, right? For checking a linearity and equality of variance, right? If the scatter diagram look like this or this, we can say that it's a linearity assumption is met. If you look at this, like this shape, quadratic or inverse quadratic, so it's not linear lah. So then, for assumption of equality of variance, same as a linearity lah, right? So if you look at this and this, then it should be equality of variance assumed. Now, if you can look at this scatter diagram, we can say that the equality of variance assumed and the linearity of assumption also assumed, right? Now, let's look at the second assumption, normality assumption. So we're going to look at the normality assumption based on histogram, right? Let's say I'm going to create the mean of pre-final for histogram residual, right? And standard deviation. I'm going to create histogram with the scatter, with the normal distribution curve, pre-final, and then put the residual, and then histogram. I'm going to create histogram, pre-final, residual, right? And then I'm going to put probability is equal, probability equal to true, and then I'm going to put in density, means that I'm going to make it the color is not really thick lah. I'm going to make it a light color, 16. And then I'm going to put the title of the graph, means the residual distribution for preliminary final model. Oops. Okay, x as this should be residual, right? And then color, maybe I will put adjust the color using this color, F1 F7 DE, right? So then I'm going to create a curve, denorm, right? Denorm x m1 std, right? And then I'm going to create a color equal to dark blue, make it thicker, lwd equal to 2, and add equal to true. Yep. So based on the histogram, we can say that the data residual is normally distributed lah. We can also check with Shapiro weak test, pre-final model residual. It will also, but in this case, Shapiro weak test shows that the p-value is less than 0.05. But the data is, we can see by eye, is normally distributed. So let's try to look for others data set. Well, for others what we call as normality test lah. Let's look at for Lily 4 test. Lily 4 test is by using library Northwest not test, right? And Lily 4 Lily test, and if I'm not fine, pre-final. Sometimes it, oh yeah, Lily 4 also give not normal, right? But by distribution, by histogram, it shows that the data is normally distributed lah. Let's try with others. If you're not confident with Lily 4, we can also try with to look by QQ plot, QQ norm, pre-final, residual, right? And then QQ line, pre-final, residual, right? So it confirmed by eye, and by eye we can say that the data is residual is normally distributed. But when you use test, right? When you use test, dia nampak macam tak normal lah, right? Okay. Let me try to find this statistical measure dulu, right? Let's say kita tengok maybe kita tengok Anderson-Darling test pre-final. Maybe you will agree. Yup, it also says that it's not normal, right? So something wrong with the test, but maybe I'm not sure, but we can say that the data is slightly skewed, kan? Ataupun nampak normal tak? I nampak macam normal, but kalau kita tengok histogram itself, right? Dia nampak, okay, I see. Alright, kalau histogram itself, you see, dia nampak macam skew to the right, to skew to the left distribution lah. Right? That's why all the test says that it's not normal, right? So in order to use multiple linear regression, you need to make sure the data set, the residual is normally distributed lah. So now let's check for the next assumption number 4. Where is it? Yeah, fit independent numerical variable. So to fit independent numerical variable, which is checking linearity of independent variable. So we're going to use xi, yr. So means that xi, x as it should be the independent variable with a numerical independent variable, and y as it should be residual. Right? Plot. So data 1, let's say h, right? And then pre-final should be residual, right? So if you look at this one, you can see dia nampak macam linear juga kan. So memandangkan kat sini saja yang tak ada apa-apa, but it seems that linear, right? So the first h is also linear. Let's say data 1, weight, pre-final, and residual, right? So kalau nak tambah sikit, let's say app line, so I tambah guna ni, this one I copy this one, letak sini, so boleh nampak dengan jelas lah. So nampak tak? So dia around zero value lah. It's around zero value. It's okay, right? Alright, it's around zero value, right? Plot data 1, and then we choose height and pre-final, right? All the independent variables should be tested lah, right? Okay, it's around zero and should be okay lah. Okay, so then once you already check for all the assumption, so we're going to create a final model, right? Instead of by using the model, the preliminary final model, also we can check all the assumption. Let's say we're going to look at number 4, checking all assumption using model plot, right? So we're going to plot. So before you plot the model, let's say I'm going to change par mf row equal to C22, means that I'm going to plot it 4 graph into one canvas. So I'm going to click plot pre-final, right? So if you can see here, the normal QQ plot shows that it is nearly to normal distribution, but it's a bit skewed here. That's why when you see the normality test is very sensitive, right? When you see the skewedness of the sikit skewness, they akan kata it's not normal. But basically when we see using a histogram dekat sini, we can merely say that this is normal lah. We can accept it as a normal, even though it's a bit skewed, but it doesn't matter because the sample size is very large for our model. Let's say we look at the dimension of data 1. So we have 1369 observation. I think it should be okay lah. We can accept it as a normal distribution, but even though it's a bit skewed, normality diagnostic test is very sensitive, so you should be very careful by using normal diagnostic test lah. So you should always compare the normality by eye, means that by presentation, histogram, box plot, or QQ plot, and so on, by a normality test. If they have agreement between these two men is confirmed. But if they have a discrepancy like this, we can make our judgment based on the graphical presentation lah. So based on this graphical presentation, we can say it's a bit skewed to the left, but we can accept it as a normal distribution because the data set, the observation is 1369. So if you look at into the central limit theorem, it says that when the data set is more than 30, some books says have more than 50, 200, 500, it is we can say that the data is approaching to normal distribution, right? So it doesn't matter. So now by looking at the I'm going to show this one, right? So based on the model based on pre-final, this is a XPYR, this data plot. So we can say that the data is linearity assumption is met, equality of variance also met, and the normal distribution also met, right? So then last step, we can establish the model. We can get the final model. So we can set our final model, right? So final model should be LM, all the variable PAFR, age plus weight plus height, right? So summary, final, and confine, final, right? So this is the confidence interval, right? So this is the final model. So if you look at this example, it's very it take all variable, right? So now your task is your task to do MLR, multiple linear regression, for USA household .csv dataset. Do we have that in the? I already input it into our Google Classroom. USA housing dataset. Try to do this task, right? So now let's look at the last step. Once you already find the final model, then we need to do report the model lah. So checklist for reporting multiple linear regression. The relationship or the purpose of the analysis. We need to be clear what is our relationship and what is our sample size. And the method of analysis is multiple linear regression. Regression coefficient, they are 95% confidence interval, the actual p-value of each independent variable in the final model. The coefficient of determination, we also need to identify lah. Based on this one, the coefficient the coefficient of determination is here lah, is 0.1624. Alright, so I already taught you to read how to read the value inside the model in simple linear regression. It's also same, right? Confirm the assumption that are fulfilled. This is the thing that you need to input into your reporting. Inform about the interaction in multicollinearity problem. Report how any outlying data treated, right? Name the statistical package used in the analysis, right? So now this is how we present the result. Let's see, I make it bigger. Now this is a presentation scale. First you need to input all the simple linear regression result and multiple linear regression result. The trick here is, kalau you nampak dekat sini, since all the variable are included, so I include all the variable inside the table. If you are doing, let's say, the variable age is not important, so you only report weight and height. The simple linear regression for weight and height, and multiple linear regression for weight and height only, right? So make sure you listen carefully about that. And then since this is all the variable are important, so beta crude regression coefficient, so A is a crude regression coefficient for simple linear regression, and for multiple linear regression is adjusted regression coefficient. We include a 95% confidence interval and the p-value, right? So if you notice, nanti I tunjuk. And then you need to describe lah forward multiple linear regression applied. Model assumption are fulfilled. There are no interaction among independent variable. No multicollinearity detected. Coefficient of determination R square is equal to 0.162, and the estimate final model equation. This is a equation lah. And then kalau you tengok dekat title, the association factor of PAFR among patient admitted to HUSM with the number of sample size. That's how we present the data lah. And then you start on interpreting the data. You can read this one, right? Interpreting the data one by one lah, right? Okay, so now kalau you tengok dalam library GT summary, right? GT summary, remember I already introduced to you a GT summary library kan, right? Still remember, right? So let's say TBL regression, so final, so it will give us the reporting lah, right? So reporting same as this is for a multiple linear regression lah. So let's say kita nak include sikit bold P, bold P value, right? It will bold the P value, right? And then bold label, right? It will bold the label, right? Okay, I think that's all for multiple linear regression. Multiple linear regression node plus PFR. Right. So do you have any question before we end our session? For your reporting, I will check later, right? Maybe this evening I will check everything, right? Yesterday I don't have much time to check. This evening I will check everything. Other than that, ada soalan before we end our session?
Yang USA housing tu kan?
Ya.
Kita buat sampai yang ni ke, yang setunjuk yang table regression ni ke?
Sampai ni, sampai final.
Oh, okay.
But for regression tu, right? Let's say, I try tengok. I dah buat dah sebenarnya, nanti I tunjuk. I nak you buat dulu, sebab I dah buat dah. Sekejap, I nak you excludekan the variable yang not important. Variable yang not important is variable number 7, right? I think. So let's say I try to data 1 and data 2 read.csv, right? So names data 2, right? So address is not really important, right? Because kalau kita tengok head data 2 is it's not numeric lah kan, it's address kan. You should exclude this variable in the model lah, right? So my advice is before you start with simple linear regression to multiple linear regression, So nampak tak dia punya variable names ni sangat panjang. You should rename the variable names, right? Make it shorter, right? So you can understand and call the variable easily. Like for example, average area income we change to income. Area house age saja ke macam tu lah, right? Ada soalan lagi? Soalan before we end our session?
Setakat ni tak ada, sir.
Alright, good. So if you don't have a question, then we end our session here. Okay, Assalamualaikum.